Good afternoon, everybody. Welcome in. Thank you for joining us today. Just a quick reminder to please silence your cell phone if you have them on, and to please do the survey at the end of the talk, which will be emailed to you automatically. That's really helpful for me to improve on my speaking, as well as for the conference. But let's get started. This is Match Cuts in Immortality, aka Programming a Tiny Scorsese. But before we jump right in, a little bit about who I am. My name is Connor, and I am the technical director at Half Mermaid. We are a Brooklyn-based studio founded by Sam Barlow, my boss, well known for his work within the narrative space, from Silent Hill, Shattered Memories, to the award-winning Her Story and Telling Lies, and now our most recent release, the game we're here to talk about today, Immortality. So let's jump into it. Immortality, the centerpiece of this talk, was released last year, August of 2022, and it's been the recipient of some incredible reviews and awards that have really blown us away and just been truly humbling, especially for me, having this be kind of the first project I jumped on fresh out of school, and being here talking to you all about it now is pretty surreal and awesome. So thanks for being here. Thanks for letting me have this moment to chat with you all about the development process. Hopefully most of you have already played Immortality. If not, I am going to do my best to keep our secrets and not spoil anything narratively. But we are going to talk in some detail about the design and structure of the game, especially with what is related to the match cut mechanic. And there may be even some lines of code that we'll see that could be vaguely spoilery. So I apologize for that. But I do think it's all going to be worth it, as a little context is going to help us a lot down the road as we get into the nitty-gritty of the technical implementation. So now, what is Immortality actually about? It's about exploring a cache of footage from 3 lost films, which were never released. Here we have a still from the first film, Ambrosio, with which is a lush period drama filmed in 1968 and adapted from M.G. Lewis's Gothic novel, The Monk, which, side note, is a really fabulous novel if you like melodrama and nuns. The second film, Minsky, is a noir-style thriller filmed in 1970, and it's about a detective investigating the murder of a famous artist and the muse who is suspected of killing him. And finally, the third film, Two of Everything, is a thriller shot in 1999 revolving around the lives of a successful pop star and her body double. So the player is presented with this lost footage from all 3 films, which includes everything from rehearsals to BTS footage to interview clips, the whole gamut. And while the years between the films means the technology, the shooting style, and the aesthetics varies greatly between them, they do, as some of you might have noticed from the previously shown stills, all have at least one thing in common. They all star the same actress, Marissa Marcel. Marissa was an up-and-coming star, seemingly destined for success in Hollywood, but her life and career were shrouded in a sort of mystery. And after filming Two of Everything in 1999, she went missing. The player's objective in sifting through the remnants of Marissa's tragically incomplete career are quite straightforwardly to answer one question: what happened to her? But of course, we don't just hand the player all of the footage at once and say good luck. Instead, the player starts with a single clip and is left to discover the rest of the footage in a way that is singularly unique to them. This means seeing things out of order, rapidly moving between scenes, genres, watching and rewatching footage with new understanding when the player gains new context, and building all of these disparate parts into some kind of whole, into a mosaic of sorts that not only helps explain what happened to Marissa, but also reflects the player's progress and their own cinematic sensibilities. And that's really what the design of Immortality came down to: cinematic sensibilities and our deconstruction of them. So how do we allow the player to find new footage in a way that encourages that cinematic eye? And how do we do it in a way that is engaging, not despite its non-linearity, but because of it? We wanted something that put the player in the seat of a director or a video editor without just recreating the tedium of working in something like Adobe Premiere. And we wanted it to challenge the player's expectation of how video playback even is supposed to work. From all of these design challenges that we set for ourselves arose the solution that became sort of the central pillar of Immortality's gameplay. And that solution was the match cut. So whether or not you've heard of it by name, I'm willing to bet most, if not all of us, have seen many, many examples of match cuts. If you haven't, you can probably gather just by looking at these examples what a match cut is. It is a film editing technique where one shot of an object or action cuts to another shot with the same or a visually equivalent composition. And these are just a few examples that I personally really like. We have Indiana Jones and his hat, infamously. A really cool shot from The Graduate on the top right. Probably kind of the best example of a match cut is the bottom left. We have this shot from Psycho. And then the bottom right is from Breaking Bad, and I just find it really viscerally gross because it's a dripping dirty pipe, and then it cuts to a cup of tea. But this is it. This is the idea we've landed on for what we think is going to satisfactorily answer all of our design challenges. We're going to let the player move through Immortality using match cuts. But what does that actually mean or even look like in a game? Oh, it looks like could not load YouTube player. Cool, cool. Well, let me see if I can get this to load. I don't think I can. I'm like so afraid to mess with the window because it took a lot to get this window to full screen. Let me pull up really quickly this clip. Okay, this looks terrible, but this will give you the idea, except it's not showing up because this is full screen. Okay, well, hopefully most of us have seen what the match cut looks like. If not, I guess use your imagination based on this, with the idea being that essentially if the player clicks on something in the scene, the camera zooms into that thing, crossfades to something else that matches the original thing that the player clicked on, and then seamlessly fades out. And that's what it looks like. All right. Here we go. So now that we all kind of have a shared understanding of what this needs to turn into, sort of, let's move backwards and explicitly break down in layman's terms how this mechanic should work as if we're putting its design down onto paper for the first time. First and foremost, the player needs to be able to select or click pretty much anything on any given frame of footage. Within reason, of course. Something that is flying across the screen or so blurry the player can't tell what it is probably not particularly useful. But any actors, props, set pieces, or even gestures, such as a kiss or hand holding, these are all game. And just so we all have a simple way of referring to these clickable things, I'm going to refer to them as symbols from here on out. Now, the next thing the code needs to be able to do is quickly compile a list of all other matching or closely matched symbols for the symbol our player originally selected. We can have exact matches, for example, an apple match cutting to another apple, or we can have a close match, meaning Marissa Marcel playing the role of Franny can match cut to Marissa Marcel playing the role of Matilda, or an apple can even link to an orange because the code has some way of understanding that there's some sort of equivalence between two pieces of fruit, right? Next, the code needs to be able to look at some data representing the player, their choices, their progress, their playstyle and interests. And from this data, the code needs to make a decision about which scene the player should be match cut to. Finally, the match cut as an exploration tool falls pretty flat if the match cut itself looks really bad. So the code needs a way to decide at which point in a clip a match cut should be able to happen. If we drop into scene 32 at the 50-second mark, for example, we want the code to consider whether the vase that we're cutting to is even on screen, or if it's blurry or tiny or obscured. All of those small but numerous choices that a video editor or director might intuitively make when cutting together footage in the editing room. So now, having our design roughly written out, it's time to get into the nuts and bolts of how we brought each of these design components to fruition, starting with making everything selectable. And this was really the aspect of immortality that had us stepping back and asking ourselves, is this actually going to be possible? It turns out it was. And while we've been asked before if it was some kind of AI under the hood that learned to recognize all of these individual symbols, it's actually much simpler and more tedious than that. To borrow Sam's own words on the subject, sometimes the solution to a complex problem is just doing a massive amount of work. And that turned out to be the case here as we started to wonder, do we actually just need to individually track every symbol that we think is worth clicking on? And that is, in fact, what we ended up doing. So after testing things out on some sample footage, we first created some lengthy documentation that put very explicit rules in place for exactly how these symbols were to be tracked. We needed to, for example, ensure that consistent naming conventions were followed so that we could accurately parse data or use it usefully across design spreadsheets or convert it into game data down the line. There needed to be rules for masks that exited out of frame so that our code could understand the difference between an on-screen and an off-screen symbol. We needed to make sure that every polygon tracking a symbol was made up of no more than 4 vertices and that they maintained the same number of vertices across the entire clip. This was necessary for several reasons, one of which was just the optimization of the already massive text files that our exporter was going to be spitting out. And it was also going to make a huge difference down the line for the real-time geometry that we would be doing for things like calculating the cursor position for the aim assist feature on controller, or dynamically determining how to handle symbols that are overlapping or obscuring one another. These were just some of the many rules established by that documentation, but you get the idea. The next step involved Sam and our producer, Natalie, marking up a single frame from each clip to indicate which things in a scene should be tracked. And first drafts would look a lot like these frames that you see. For our third step, we had a team of incredible rotoscoping superstars who would receive the marked up drafts from us and then track the indicated symbols across the entirety of every clip in Immortality, following the rules of our documentation. And then finally, after getting those After Effects files back, the only thing left to do was to run a simple exporter script that would spit out the data into a text file format. And I'm not going to really go into specifics on the exporter script, but in general terms, the way this data was exported was by looping through each mask in the After Effects timeline. And if you're unfamiliar with After Effects, masks are essentially the polygons that act as tracking components, and each mask's positional data would then be copied over from each frame of footage, specifically the X and Y coordinates of each of these masks' vertices. All that info was then written into a text file, which looked a lot like this, a giant wall of text. This particular file is first seen from Minsky, and at the top of it, we've got some basic info from the footage itself. This data was more so pertinent for video playback in particular, and it includes things like the duration of the video clip, the video resolution, the frame rate, in this case, 24 frames per second. Although, fun fact, we did decide to give ourselves the bonus challenge / headache of having different frame rates across all 3 of the films in Immortality. Then below that, we see kind of this endless string of characters that upon closer inspection, we can actually see make up the data we need for tracking the symbol hand_lighter. We have a color in the format of a normalized RGB, which determines the color of the polygon drawn around each symbol. Obviously, you don't see these polygons in the finished game, but you can imagine their value in debugging. Then below that is key 1 at 0, which essentially means the first frame at a timestamp of 0 seconds. And below that is a very long comma-separated list of decimal numbers, which, if we take these numbers and split them into pairs, suddenly look a lot like 4 vector 2s, each with their own X and Y coordinates. And in fact, these coordinates make up the 4 vertices that create the path around our symbol hand_lighter. And if we were to actually plot these vertices over the first frame of the video clip, we get a mask that looks something like this. So I'm going to gloss over actually importing the data from these text files into the game engine because it's just a lot of string parsing. And we have a lot of other code to get to. But having imported this data, we now have what we need for tracking our symbols, for ensuring that every interesting bit of imagery will be interactable. So let's move on to tackling our second design challenge, which, as a reminder, is finding in real time a list of all the matching or nearly matching symbols for anything that the player has clicked on. Finding exact matches should be straightforward, right? We can simply do a string comparison of the symbols by name, but how does that code decide whether or not an apple can link the player to an orange? Well, before we fire off our search function, we need to gather a bit more data specifically for this, for non-exact symbol matches. And this is done at the time of import by cross-referencing and pulling data from a monstrous spreadsheet. This one in particular is our symbol spreadsheet, and it did its fair share of heavy lifting in Immortality. It's where a lot of design choices were made, especially those that required a bit more critical consideration, such as the choice of which symbol could and should match cut to which in the case of non-exact matches. These non-exact matches we called valid links. And while this sheet was actually, fun fact, populated by our importer script using Google API, this column of valid links was populated by hand by Sam and Natalie, who would make the final call on whether a hand should be able to not only match cut to another hand, but also to a glove or to someone clapping or to a middle finger. So now that we have a way to find the partial matches through our valid links, I'd like to break down how all the data we've imported is organized and structured in game. This way we have kind of a shared understanding of various classes that are going to come up a lot in the next several slides. We start with a scriptable object called metadata, and this is the root of everything we care about, the motherboard of our whole operation. And within metadata is a list of video data objects and a list of video link data objects. We'll pull the curtain on both of these, but let's just start with video data. So the video data class is a structure for containing all of the info for a single video clip. So for the full list of video data objects within metadata is 288 items total, one for each scene in Immortality. Within each of those is a list of mask data objects, which contain information for individual symbols that appear within the video clip referenced by our video data object. Lastly, our mask data objects each contain a list of key data objects, and each key data object just contains that positional tracking info that we've imported from After Effects before. Now, it's one thing to hear me rattling off all of these things by name. It's another thing to visualize what it all means in context. So I'm going to just quickly show how this translates visually. A video data object is just for a particular video clip. So let's say we're looking at the video data object for clip 32, which is an Ambrosio scene. There will be all sorts of information for the video itself in this object, frame rate, duration, file name, etc. But we just care about the list of mask data objects right now. And our list of mask data objects is essentially just a list of the symbols that appear in clip 32. Given that it's an Ambrosio scene, we're unsurprisingly looking at mask data objects for symbols like Ambrosio _ crying, candle _ lit, cross _ Ambrosio, and so on. And each of these symbols has a list of key data objects, which just tells you where a symbol exists on the screen at any particular moment in time. So this is all the data we access so that our symbol is tracking smoothly and accurately down to the frame, hopefully resulting in something like this GIF of Ambrosio picking up and putting down a vase over and over again. So now let's take a look at our list of video link data. Video link data pertains to symbols. And while this might sound redundant because we just established mask data objects also reference symbols, the distinction here is that mask data is for specific instances of symbols within videos, and it contains the necessary data for tracking those symbols, while the video link data is essentially a lookup list of all the symbols that appear across all of Immortality. And it contains information relevant to our match cut transition. Specifically, within each video link data object is a list of video entry data object. And this is a list of every video that a particular symbol appears in. However, video entry data objects don't actually care about any info related to the video clips themselves. They only care about their lists of entry point data. which is, simply put, some information on when and where to cut to a particular symbol within a given video clip. Again, I'm throwing a lot of words out there, and in particular, I think maybe the words keyframe, symbol, and data are starting to lose their meaning. So I'm going to rely on some more visualization. Let's say we grabbed a random video link data object, and it happened to be a vase. Not a particular vase, but a vase as a symbol. And our list of video entry data tells us that the symbol vase appears in 13 different clips, scenes 24, 32, 40, lots and lots of vases in Immortality. And now we look specifically at the entry point data for scene 32. We get data for a single frame in that video. And this data, which you can see kind of the class for here, is just telling us, hey, this is the timestamp in this clip when the vase is going to look its most beautiful for a match cut. And this is where on the screen that symbol positionally exists at that time. Now, how we actually picked this particular entry point is a different discussion, but we will get to that shortly. For now, let's get to the actual method responsible for finding matches. This method is called doSearch, and it's fairly long for a single method, so let's just zoom in and break this down piece by piece. So we've defined this as a public method. It's going to return a list of something called database result. And all that a database result is just a temporary data structure that's going to hold some references to a valid and matching symbol if and when we find one. Specifically, references to data that we're already familiar with, such as mask data, video data, and entry point data. Now, returning to our doSearch method, we can see it takes mask data as a parameter, specifically the mask data for the symbol the player has selected. And it also takes video data as a parameter, and this would be for the video data for the footage they were watching when they selected that symbol. Now, the first thing we do is prepare some lists to hold the rest of the results of our search. We have link data results, which is a list of video link data, and final results, which is a list of database results. And then given that our game data isn't null, and our game data here is just the name that we've given to our metadata object, we move into the meat of this function. And we're going to start by ensuring that the name of the mask passed into this method is stripped down to its most base form. And the reason for this is that many scenes in Immortality have several instances of the same kind of symbol in them. For example, many of the Ambrosio scenes have dozens of candles that are individually tagged and tracked. And in order for the code to be able to differentiate between them when it needs to, we append the mask names with a hyphen and a number when we import. So we might have candle 1, candle 2, etc. And while that's great for differentiating, here we're actually about to do a lookup in our video link data list. So we need the symbol's name with nothing appended to it. Having done that, now we use the mask name to search for an exact match. And if one exists, then we add it to our list of data results. Next, we're going to look for any partial matches. And this is where we get to access that fabulous list of valid links that we pulled from our design spreadsheets and loop through each item it contains. For example, if the player clicked on Marissa, then within the list of valid links for the symbol Marissa, we might find Franny, Matilda, Maria, or any other roles played by Marissa. Remember that our list of valid links is just a list of strings. So using each valid link, we then do a lookup to find the corresponding video link data object and add that to our list of link data results. You'll also note that we do a quick check to ensure that the valid link is not an exact match for the symbol the player clicked. This is because we've already added the exact match, and doing so again, as we found out the hard way, would mean there were duplicates in our list of results. And later on, when we're scoring those results, having duplicates of one is going to unfairly skew the outcome of which symbol is going to ultimately be selected for the match cut. Now, of course, a symbol shouldn't theoretically be listed as its own valid link in the spreadsheet, but as you'll remember, our valid links column was populated by hand. And so human error means that the code should just be prepared for mistakes it can easily correct, especially as it's a lot easier to add one line of extra code than it would be to tell our designers to go and find those entries by hand in the spreadsheet and fix them. Now, we've compiled together all of our link data results, but these are just references to symbols generally, not to specific instances of them just yet. So our next step is to loop through each video entry data object for each result. In other words, we've got our list of symbols for Marissa, which include Marissa, the exact match, as well as Franny, Matilda, and Maria, our partial matches. But now we go one step further, and we get the list of each instance of those symbols throughout the entire game. So looking at the video link data result for Franny, we loop through each video entry for each video clip in which Franny appears and ensure it passes a few checks. The first thing we're going to check is whether or not the video entry for this symbol has any valid entry points, meaning is there even a defined place in the video to which we could match cut to? In almost all cases, the answer to this should be yes, but there are a few edge cases, perhaps if a symbol is only on screen for a single second, where we haven't defined any entry points, because match cutting to something that is on screen that briefly is going to look really bad and feel really disorienting for the player. Now, assuming we do have a valid entry point, the next thing we check is whether or not the video entry is supernatural. I'm not really going to get into what supernatural means here, just to try and spare anyone from spoilers. But suffice it to say that this is just a flag, and we need to ensure that the video clip is not flagged as supernatural, because internally the design decision was made that the player should never be able to match cut to anything that is. And finally, provided that we've passed the previous two checks, we check whether or not the player is gated from accessing this particular video. There are very few gated videos in Immortality in general, but a handful of them are so central to the narrative and require enough context that the decision was made to ensure that the player has seen some amount of content before being able to access them. So having jumped through every hoop, we now grab the relevant mask data, video data, and entry point data for every result that passed our tests, and we plug them into a new database result, which is added to our list of final results. Now, by the time we've looped through every video entry for every link data result, we should have gathered together a totally comprehensive list of all of our match cut options, which we then return. So that takes care of finding eligible symbols for any given match cut. Our next step is choosing a single option from the results of our search and making that choice as specific, interesting, and expressive as possible. And this right here is kind of the magic of Immortality, because where this could feel totally out of control and random, and in fact, there is some randomness built into it very intentionally, it actually is very personalized. And the way we achieve that personalization is with an algorithm that looks at each result found by the search function and then scores it according to what we know about our player's journey thus far. And that algorithm is contained within our score result function. While it's not an outlandishly long function, let's make this easier and go ahead and zoom in once again, piece by piece, starting at the top. So we know it's going to return a float, presumably the score for the database result we pass in. And in addition to that, we will also be passing in the video data and mask data for the symbol the player originally selected, as well as an enum called sort option, which I'll expand on in just a bit. And finally, a float called completion score, which is just a normalized number representing the player's progress in the game. Now, the first thing we need to calculate as a part of this algorithm is the target clip affinity, which is just a fancy name we've given to a float that represents how aligned the clip's themes are with the themes the player has thus far been most in tune to. But let's just pull back for a second, because I'm talking about themes now, which we've never mentioned before. So to clarify, Immortality actually has three core themes that have been defined in its design: religion, moment, and art. And each scene is therefore assigned a vector-3 value that tells us how representative it is of each theme. For example, a very literal interpretation of this might mean an Ambrosio scene would be ranked very high in religion because it's about a monk and takes place in an abbey. So to calculate this, we take the dot product of the video clip's theme score and the player's theme score. In general, the more aligned two vectors are, the higher the dot product. So the more the result we're scoring is aligned with the player's theme score, the more the result will ultimately be favored, meaning that the game kind of tends towards encouraging the player to pursue narrative threads that they've already shown they're interested in. Next, we calculate what we're calling the supernatural multiplier. And this is essentially a Boolean, but represented as a float. Specifically, if the video clip for the symbol we're scoring has any supernatural secrets, whatever that means, then the supernatural multiplier is 1. If not, then it's 0. And this supernatural multiplier is used in calculating another variable, the supernatural affinity. And this is simply put a value that just indicates how recently the player has encountered a clip that does have a supernatural secret. We calculate this using something called the freaky score, which is a very technical name that we came up with, but it's also a value that we track and update every time the player watches a clip. The longer the player goes without encountering a supernatural secret, the higher the freaky score. We then multiply the freaky score by the supernatural multiplier we calculated before. In other words, if it's been a while since the player has seen anything supernatural, and if the clip we're scoring does have a secret, then our supernatural affinity is going to be higher and will weight the overall scoring to be in favor of this clip. This ensures that there's some regular pacing when it comes to encountering these mysterious events. Next, we calculate the progress affinity for this result. And to do that, we first need the clip importance value, which is a static score between 0 and 1, indicating how essential a clip is to the overarching immortality narrative. We also need the target clip affinity that we calculated earlier relative to the completion score, aka how far the player has progressed. Once we have these values, we can do a simple comparison and set our progress affinity equal to the lesser of the two. What this does is ensure that we don't actually front load all of the heavy important scenes at the beginning of the game, because this mathf.min comparison acts essentially as a clamp. So the less the player has progressed, the smaller the second value is in our comparison, which will win over any high clip importance values. Then as the player progresses further and that value increases, they'll naturally start to encounter more and more important meaty clips. Like our supernatural infinity, this is just more handy math for narrative pacing. Following progress affinity, we have a very straightforward value, fresh affinity, which is just another Boolean represented as a float. And it simply weights the scoring such that clips which have never been seen by the player, meaning fresh affinity is equal to 1, are more favored than clips that already have been seen. Now, this next bit of code should seem a little familiar. Here we are calculating our exact match modifier value, and all we're doing to calculate it is comparing the name of the mask the player selected to the name of the mask we're scoring. And if they're an exact match, our exact match modifier will be equal to 1, meaning that our scoring algorithm will end up slightly favoring any results that are exact matches over those that are not. And this next bit for calculating what we call proximity affinity is kind of taking up a larger footprint, but the result is pretty cool. So if you'll remember from earlier, we passed an enum called sort option into our score result function. And sort option is just a group of IDs representing how the player can have their video grid organized. Really, there are only two options. The grid can be sorted either by date, meaning when the footage was actually shot, or by slate, meaning by the film and scene number, which should theoretically translate to being the chronological order of the film's timelines. So depending on the sort order the player is using at the time, score result is called. We can either calculate the distance between the date of the video clip the player came from and the date of the video clip we're scoring, or we can calculate the distance between the two video clips in terms of their film and scene numbers. The closer together the video clips are, either by date or cinematic timeline, the more that clip being scored is going to be favored in the final algorithm. The last thing we're going to take into account for our final scoring algorithm is how many times the player has seen the clip we're scoring within the last 10 clips that they've most recently seen. So for every time in the last 10 views that the player has seen the clip we're attempting to score, the code increments that counted views. And as sort affinity is calculated as 1 over the number of views, plus 1 to ensure that we never divide by 0, sort affinity becomes significantly smaller the more the player has seen the given clip. So if we're dealing with the result that the player has seen a lot of recently, then the final scoring algorithm is going to greatly disfavor that result. And speaking of the final scoring algorithm, here she is at last, making the overall score for a given database result this. Or in case you forgot what any of these variables are, here's a version of the algorithm translated loosely to natural language. And you can see by the multipliers here too, how certain components of this algorithm are weighted and prioritized over others. Fresh affinity, for example, which attempts to favor clips the player has never seen, is the most highly weighted, with sort affinity and progress affinity closely following. So now you know how we calculate the score for a possibly matching symbol instance. And this is how a single scored result is finally selected. As each possible match is scored, that score is plugged into an array of floats called weights, and this is then added to a value used for tracking the cumulative total of all the scores, total weight. Having scored everything, this is where the randomization comes in. So using the current time in milliseconds as a seed, and this is to ensure that we're never caught in a pattern using the same seed each time we call our search method, we create a new pseudo-random number generator and generate a number between 0 and the total weight. From there, we loop through our weights, which is our list of scores, tracking the cumulative weight once again through each iteration, until we find the index where the random number we generated is greater than the accumulated weight thus far, but less than the accumulated weight plus the score at the current index in our loop. And using that index, we find the corresponding database result in our list of results and return that as our final choice for our match cut. The weighting in this implementation, therefore, makes some symbols far more likely to be selected than others by virtue of scoring them higher. And a higher score means a wider range in our weighted system. And a randomly selected number is just statistically more likely to fall within a range the wider that range is. But even with the weighting, the randomness still means that nothing is guaranteed, right? No matter how statistically likely. We've created sort of a nice bell curve of somewhat knowable behavior, but with enough unpredictability to create a unique experience for each player. And now, all that's left is just ensuring that the match cut looks seamless and stunning. Piece of cake, if this was the cake I was referring to. Well, perhaps not that bad, but there were a lot of layers to deal with in determining the entry points for these match cuts through code, and there were months of trial and error before feeling we'd gotten it exactly right. It was really something that we were working on and tweaking from the beginning to the very end of development. I'm not going to walk through every line of it just because there's too much to get through in the time that we have left, but we are going to look at some modular bits that I think are going to give you the right idea. And so in trying to figure out how to select the right point for a match cut, we really sort of asked ourselves the question, what makes a match cut look good? And also what makes a match cut look bad? And the first answer we thought of was a pretty easy win. We need to ensure that the symbol is on screen at the time of the match cut. The way we did this was by checking the position of each vertex for a symbol against the frame size, which is really just the video resolution. If all the verts were on screen, fabulous. Or if even a single vert was on screen, then the symbol was also considered on screen for that given frame. Where we ran into some issues when we realized that there's actually a third scenario where the symbol itself could technically be on screen while none of its vertices were. So that led to some fun head scratching. For this specific scenario, we had to add a stipulation to the method. Given that all the vertices had failed the check that they were on screen, we now had to take 2 vertices at a time and test whether or not the line that they formed intersected with the bottom, top, left, or right of the screen. If so, our symbol must be at least partially visible on screen. If not, however, and the symbol is found to be truly off screen for a given keyframe, then that keyframe is thrown out of the running for being a match cut entry point. Having determined whether or not a symbol was on screen also enabled us to group keyframes into sections based on when we knew the symbols entered and exited the shot. And what I mean by this is, if we have this amazing Oscar-worthy scene of this apple, and it's moving from the left of the screen to then exit off to the right of the screen. And then we have this chunk of the clip where there's just no apple. and then it comes back on and goes the other direction, we know that obviously those frames without an apple are useless. So we toss those out. But what that also means is that we can leave these apples kind of separated into their own sections of frames, which is going to really be useful to us in the next step, which is ensuring that we're not selecting an entry point where the symbol has just entered the scene or is about to exit. So you can kind of see an example of this here. The woman on the very left of the screen, we actually got some really weird results for until we kind of accounted for this, because she's literally on the screen for just a very short moment of time. The reason for this, as one might imagine, is because zooming in and crossfading to a symbol that is about to fly off or onto the screen is going to look and feel pretty bad. So to keep this from happening, we wanted to take our new keyframe sections and eliminate any keyframes from them that are too close to either the beginning or the end of each section. Doing this is straightforward. We simply loop through each section of keyframes, caching the timestamp of the first and last frame in each. These become our entry and exit times for a section and are our point of reference for comparing against other frames. Next, looping through keyframes in a section, we calculate the distance in seconds between each frame and the exit time, and between the same frame and the entrance time. Given that the keyframe is no closer to the entrance time than our minimum distance threshold, a constant that we found kind of works most reliably at about 0.15 seconds, and that it's no closer to the exit time than our minimum distance from exit threshold, which is another constant set to 0.4, then that key gets to remain in the section and is still eligible as a match cut entry point. Otherwise, we eliminate it from the running. I can see that I'm going over, so I'm going to fly through these really quickly. The next step was ensuring that the symbol meets the size minimum, because if we're zooming into something like this, it's going to look like a little blurry mess that we don't even know what it is. And so to do that, we just quite simply checked if it was big enough. Easy. And then finally we got to select a key. So having checked that, okay, it's not too blurry, it's not too close to entering or exiting the frame, and it is on screen, the next thing we said was, let's just pick a frame where the mask is fairly large, and if we can, where the subtitles from actors speaking are not on, just because that makes it a little bit cleaner. And given that we found a keyframe that met those parameters, we picked it. And then that's how we did it. And that is how you make immortality. Just a reminder to do that survey if you can. Thank you all very much for coming. I'm very sorry for going over. I don't know if we're able to stay in this room at all, but if we're not, then I will go, right? Thank you. Then I will be right outside if anybody does want to chat or has any questions. But thank you all very much. This was awesome.